Hi everyone, in this video I'm going to show you how we calculate the t-statistic for the two-sample t-test that will be used to test the null hypothesis. We will continue our mass versus varied practice study where the research question is there a difference between mass and varied practice for learning how to throw beanbags into a bucket? Let's suppose we have some hypothetical data where we have 8 participants in each group. We're going to need some descriptive statistics in order to calculate the t-statistic. For example, we're going to need the mean of each group. So for example, I will arbitrarily call mass practice group 1, and the mean for this group is equal to 25.38. And the mean for the varied practice group, for group 2, 34.63. We're also going to need the variability in each group, and I'm going to use the variance. Variance in the first group is 42.55. And the variance for the second group is 45.13. We'll also need the sample size from each group. So n sub 1 is 8. And for that's for the first group. For the second group, it's the same. It happens to be 8 in this case because we have a balanced design. But we don't need to have a balanced design to run the two-sample t-test. The overall sample size is 16. So using the statistics, we can compute the t-statistic. Before I show you the formula for the two-sample t-statistic, I want to talk about the general format of all t-statistics. As I described in previous videos, the null hypothesis, we specify a parameter, and it's equal to a specific value called x. Now, in a t-statistic, what we're doing is first estimating that parameter using a sample statistic. We have a statistic that estimates this parameter. We find out how far it is from what we expect if the null hypothesis is true. And that's where x comes in. That goes here. And then to take into account the amount of error in our statistic, we divide by the standard error of our statistic. Now let's use this example to look at the two-sample t-test. The null, for example, mu1 minus mu2, that's the difference in the means, is equal to 0. Well, the t here, we're going to take the difference in the sample means as an estimate of the difference in the population means. We're going to subtract that from what we expect the difference to equal if the null is true, which is 0. Now, the fact that this is 0, which is often the case, you'll see that in textbooks they'll leave out this part here, because it's usually 0. And then we divide by the standard error of the difference in the sample means. Now, the standard error of the difference in the sample means is equal to the square root of what's called a pooled variance, we'll talk about that in a moment, divided by the sample size for the first group, plus the same pooled variance divided by the sample size for the second group. This pooled variance plays an important role in the two-sample t-test. So because it plays such an important role, I want to talk about this pooled variance. It comes from the fact that we have an equal variance assumption for the two-sample t-test. In other words, we're assuming that the variance for the first population in our dependent variable is equal to the variance for the second, which means it's equal to one number. But we have actually 2 estimates of this one number. We have a variance for the first group and a variance for the second. So what we're going to do is essentially pool these 2 estimates into one number, and that's what we're calling the pooled variance. Now, there are 2 different ways you can compute this pooled variance depending on the type of design you have. If you have a balanced design, now balanced design again is one where the sample sizes are equal to one another, and which it is in this case. If that's the case, the pooled variance is equal to the average of the individual variances. So we take the variance of the first group plus the variance of the second group, and we divide by 2. So for instance, in this case, because we do have a balanced design, the first variance was 42.55. That was the variance, dependent variable for the first group. and we add that to 45.13. And then we divide by 2, and we get 43.84. And so this number here, as a pool variance, is an estimate of the variability in the population. But what if we don't have a balanced design? What if we have an unbalanced design? This is where the sample sizes for the two groups are not equal to one another. Well, in this case, we can't simply average the two variances. Instead, we're going to compute the pooled variance by first, in the numerator, summing the sum of squares for the first group with the sum of squares for the second group. Now, this sum of squares is simply the numerator in a sample variance. So we take each observation for that in that sample minus the mean squared and summed up. Then we're going to divide by the degrees of freedom for the first group plus the degrees of freedom for the second group. Now, if you look at this formula, a variance is a sum of squares divided by degrees of freedom. What we're doing in the numerator is adding up the sum of squares first and the degrees of freedom in the denominator. Well, the degrees of freedom for first group is the number of people in that group minus 1. And the degrees of freedom for the second group is the same thing for the second group. And so what the denominator becomes is capital N minus 2. Right? And so in this case, it would still equal 43.84. So this formula actually works whether you have a balanced or unbalanced design. And when you have a balanced design, just it's easier to average the two variances. Now let's use the statistics to compute our t-statistic. Well, first we'll need the standard error of the difference in the means. We'll take the square root as we said earlier. We're going to have the pooled variance of 43.84 divided by the sample size for the first group, which is 8, plus the pooled variance of 43.84 divided by 8. Now, the fact these are 8, they're the same because we have a balanced design in this case. That ends up being 3.31. So this is a standard error that represents the amount of error in the difference in the sample means. Now we can use that to calculate our t-statistic that will be used to test our null hypothesis. We have the difference in the means, which is the mean for the first group is 25.38. The mean for the second group is 34.63. We expect that to equal 0 if the null is true. Then we divide by 3.31, and our statistic equals negative 2.79. And so we'll use this statistic to test the null. But I want to highlight here, it's negative because it happens to be group 1 had a lower mean than group 2. If I reverse these two, it would just simply be a positive 2.79. And the next thing I want to point out is this t-statistic, we expect it to be close to 0 when the null is true. And the fact is far from 0 may indicate that the null is false. But we'll, in the next video, show you how to use this t-statistic to test that null to determine is negative 2.79 large given sampling error.